Welcome back to our channel. In previous sessions, we've explored foundational concepts in machine learning, and today we're going to dive into linear regression, one of the most essential algorithms in this field. Linear regression is a supervised learning technique primarily used to predict a continuous output variable, often referred to as y, which is known as the dependent variable. This prediction is based on one or more input variables, commonly denoted as x, which are known as independent variables. The fundamental principle of linear regression is its assumption of a linear relationship between these inputs and outputs, meaning that as the input variables change, the output changes in a consistent, proportional manner. To illustrate this, consider the task of predicting house prices. In this scenario, the price of a house, the dependent variable, or y, could depend on several factors, such as its size, the number of bedrooms, and the location. These factors represent the input variables, or x. The aim of linear regression is to create a regression line that best fits the data points representing these relationships. This line is crucial because it minimizes the distance between the actual data points and the regression line, a process referred to as minimizing the error. Moreover, in the context of linear regression, it's important to note that x is dependent on y. We can express this relationship as input x, output y, indicating that the input variable's features help predict the target variable, output. The features x are used to determine the value of the target y, and this relationship is foundational for making predictions in various applications. Understanding these concepts is vital, as linear regression equips us with the tools to analyze and model relationships in data effectively, paving the way for more complex predictive techniques in the realm of machine learning. Now, let's move on to the types of linear regression. Linear regression can be categorized into two primary types: simple linear regression and multiple linear regression. Simple linear regression is the most straightforward approach, involving a single independent variable x to predict a dependent variable y. This relationship is represented by a straight line, described by the equation y equals mx plus b, where m is the slope, indicating how much y changes with a 1-unit change in x, and b is the y-intercept, the value of y when x equals 0. For example, if we want to predict house prices based solely on their size, the model would find the best-fitting line that correlates house size, independent variable, with price, dependent variable. On the other hand, multiple linear regression extends this concept by incorporating two or more independent variables to make predictions. The equation for multiple linear regression takes the form y equals b0 plus b1x1 plus b2x2 till plus bnxn, where b0 is the intercept and b1, b2 till bn are the coefficients corresponding to each independent variable. This allows for a more comprehensive analysis of how multiple factors collectively influence the dependent variable. For instance, when predicting house prices, we might consider not just the size of the house, but also the number of bedrooms and the neighborhood, allowing for a more nuanced prediction that captures the complexity of real-world scenarios. Understanding these types of linear regression is essential, as they provide the foundational knowledge necessary for building more complex machine learning models. Now, let's take a deep dive into simple linear regression. Simple linear regression is one of the most fundamental algorithms in machine learning, designed to model the relationship between a single independent variable and a dependent variable. The primary goal is to find a linear equation that best describes this relationship, enabling us to make predictions based on new input values. The equation for simple linear regression is typically expressed as y equals mx plus b. In this equation, y is the predicted value, dependent variable. X is the independent variable, input. M represents the slope of the line, indicating the rate at which y changes for a 1-unit change in x. B is the y-intercept, the value of y when x is 0. To illustrate, consider predicting house prices based solely on the size of the house in square feet. Here, the size serves as our independent variable, x, while the price is the dependent variable, y. The simple linear regression model analyzes historical data to find the best-fitting line that minimizes the difference between the predicted prices and the actual prices. This difference is quantified through a metric called the mean squared error, which the model strives to minimize during training. A crucial aspect of simple linear regression is the assumption of linearity. It assumes a straight line relationship between the independent and dependent variables. If the actual relationship is more complex, e.g., quadratic or exponential, a simple linear model may not capture the nuances, leading to inaccurate predictions. One of the advantages of simple linear regression is its interpretability. The coefficients, slope and intercept, provide clear insights into how changes in the independent variable affect the dependent variable. For instance, if the slope m is positive, it indicates that as the size of the house increases, the price tends to increase as well. Despite its simplicity, simple linear regression serves as a powerful tool in various applications, such as forecasting sales based on advertising spend or predicting exam scores based on study hours. It lays the groundwork for understanding more complex regression techniques that involve multiple variables. Now, let's start with a problem that we can address using linear regression. Say we want to predict the price of a house based on its size. To do this, we can use the foundational equation of linear regression, y equals mx plus b. In this equation, the x-axis represents the size of the house in square feet, while the y-axis indicates the price of the house in thousands of dollars. The slope m of the line shows how much the price changes with each additional square foot of size, and the y-intercept b tells us the predicted price when the size is 0, which, while not practical, helps define our line. Let's consider some example data to illustrate our linear regression problem. We have a data set that includes the sizes of houses in square feet and their corresponding prices in thousands of dollars. For instance, a house that measures 1,500 square feet is priced at $300,000, while a 2,000 square foot house is valued at $400,000. Similarly, a 2,500 square foot house costs around $500,000, and a 3,000 square foot house is priced at $600,000. This data set provides us with a clear view of how the price of a house increases as its size grows, setting the stage for applying linear regression to predict house prices based on size. When we plot these data points on a graph, we can visualize how they correlate. By fitting a regression line through these points, we can see the relationship between house size and price. For instance, if we calculate a slope of me.2, it indicates that for every additional square foot, the price increases by $200. Now, if we want to predict the price of a 2,200 square foot house, we plug this value into our equation, y equals 0.2 times 2,200 plus b. Assuming b equals 0 for simplicity, we find y equals 0.2 times 2,200, which is 440. This means the predicted price for a 2,200 square foot house would be $440,000. The regression line not only highlights the relationship between size and price, but also empowers us to make accurate predictions based on historical data. With this understanding, we can see how linear regression is a powerful tool for tackling real-world problems in real estate and beyond.